Good afternoon, everyone. On behalf of the SPE UWI Student Chapter and the SPE GAIA Sustainability Program, we would like to welcome everyone to our Hydrogen Energy Technical Talk. My name is Janae Weeks, the Energy Sustainability Officer for the SPE UWI Student Chapter, and I will be your moderator for today's talk. Before we commence, let's review some house rules for today's session. Please ensure that you've entered your full name and/or profile picture so that our presenter can easily identify you. To help keep background noise to a minimum, please ensure that your microphone is muted when you are not speaking. Your use of your camera during the session is great for interaction purposes, so video chat is encouraged. And lastly, I would just like to inform everyone that the session is being recorded so you can review this talk on the SPE UWI Student Chapter YouTube channel. Hydrogen is found in the greatest quantities in water, but it can also be found in natural gas, coal, and petroleum. Green hydrogen is produced by using renewable energy to split sustainable water into hydrogen and oxygen. So by harnessing renewable energy sources such as solar and wind in conjunction with hydrogen technology, this is a clean renewable energy that can support domestic energy needs. It can be used as a clean transport fuel for providing electricity to the grid and in factories to offset the carbon from manufacturing processes. Hydrogen energy is environmentally friendly, so when burnt as a fuel, the only byproduct is water. Now that you've gotten a little insight to what hydrogen energy is, I would like to introduce you all to our guest speaker, Mrs. Cassandra Dewan. Cassandra Dewan is currently pursuing her PhD part-time in metallurgical and material engineering at the Universidad Federal de Rio de Janeiro. Her research area is carbon capture and utilization. She has a keen interest in hydrogen energy and firmly believes that it will play a vital role in the energy transition. In addition, Cassandra holds a Bachelor of Science in Chemical and Process Engineering and a Master of Science in Petroleum Engineering from the University of the West Indies. She has over 8 years of professional experience and has worked both upstream and downstream with individuals across all disciplines and departments globally. Cassandra is currently the SPE Latin America and Caribbean Region Young Professionals Liaison, a member of the SPE Young Member Engagement Committee, and the SPE Student Paper Contest and Petrobol Lead. In 2020, she was awarded the SPE Regional Young Member Outstanding Service Award, and in 2021, she was awarded the SPE Giovanni Pacoloni Young Professional Service Award in 2021. Additionally, Cassandra is a volunteer teacher at the Cidadão Pro Mundo, where she teaches English to teenagers and adults from needy communities in Rio de Janeiro, Brazil. Now I'll pass you on to Ms. Dewan for her presentation. Thank you.
Thank you, Joanne, for the lovely introduction. Is it possible to share my screen?
Yes, I think you just have to press the share content box that's next to the muted content. Yeah.
You're seeing it now, right?
Yeah, I can see it.
Transitioning from a fossil fuel-based economy to hydrogen-based economy. So I'm just going to do a brief introduction. So the words hydrogen economy were first published back in 1972 in a paper by John Bockris and John Appleby. However, 50 years later, and we're still about another 50 years away from achieving this goal. The global demand for energy will continue to increase in the coming years and climate change. In addition, the COVID-19 pandemic emphasized the need to implement sustainable technologies in all sectors. These factors, combined with the Paris 0.5 degrees Celsius, have led to a keen interest in the generation of clean, low-carbon energy from renewable sources and hydrogen. The world is currently used today to address the challenges ahead. Hydrogen will play a crucial role both as an energy carrier and a fuel source in the decarbonization of global energy consumption. 30 countries with national hydrogen strategies and approximately 230 extensive hydrogen projects across the entire hydrogen value chain, production, infrastructure, and applications. Furthermore, hydrogen energy is atop the global political agenda, with governments allocating over 70 billion USD in public funding. However, if they really want to significantly accelerate the growth of the hydrogen economy, they will need to provide substantially more funding in addition to the stated amount. So now I'm going to discuss a bit about the hydrogen rainbow. So the universe is rich in hydrogen, which is a simple, small, light, colorless, odorless, and tasteless element found in combination with other elements such as oxygen, an example is water, carbon, an example is methane, and nitrogen, an example is ammonia. When compared to fossil fuels, hydrogen has the highest energy content per mass, 143 megajoules per kg, which is roughly 3 times larger than that of natural gas. Conversely, it also has the lowest energy content per volume at ambient pressure, 0.0107 megajoules per liter, compared to 0.0 it more energy intensive and limits its use because in addition to the energy required to produce pure hydrogen, energy is also required to liquefy it for storage and distribution.
Kind of pulls the white cell.
It is not an energy source. It is a way to store and transmit energy generated by different energy sources. Hydrogen is also fuel and can be used in nearly every application where fossil fuels are presently utilized. Example, heat for industry and buildings, fuel for transport and power, feedstock for chemicals and products, plus valorization of surplus energy from variable renewable power. The use of hydrogen, both as an energy carrier decrease greenhouse gas emissions and air pollution. Gray hydrogen accounts for 70% of the global hydrogen production. It is produced by methane reacts with steam to produce hydrogen and carbon oxides, as shown in equation 1 and 2. Its production cost is the lowest at 1 to 1.8 USD per kg. Nevertheless, its byproducts, carbon monoxide and carbon dioxide, are emitted into the atmosphere, thus negatively impacting global warming and climate change. Subsequently, gray hydrogen is not a long-term solution and should only be used at the start of the hydrogen energy transition to assist in the establishment of hydrogen supply infrastructure, as well as the commercialization of hydrogen utilization technologies. Most likely, it will not benefit from government financial incentives and is incapable of competing alongside the same fuel that it is generated from. Blue hydrogen is produced when gray hydrogen is combined with carbon capture and storage technology, therefore reducing the amount of carbon oxides released into the atmosphere. Steam methane reformation and depends on whether post-combustion CO2 capture is applied or not. Presently, SMR and CCS have a technology and ready for commercial application in an operational environment. The production cost of blue hydrogen from SMR with CCS is 1.5 to 2.3 USD per kg. This production cost is expected to decline as CCS technology continues to improve and is implemented in large-scale projects. Furthermore, it has an advantage as it builds on the industry's existing knowledge and expertise in grey hydrogen, and in several cases, the facilities can be simply upgraded by adding CCS systems. Blue hydrogen will lead the hydrogen energy transition in the upcoming years until renewable energy sources this transition by establishing financial incentives in the form of carbon tax, carbon credits, and public funding to encourage companies to install CCS jobs, consequently helping nations to recover from the COVID-19 pandemic. Green hydrogen is produced from water using electricity from renewable energy sources. Example, solar, wind, hydro, geothermal, and biomass through electrolysis. The overall chemical reaction is shown in equation 3. When electrical energy passes through water, its molecules decompose into hydrogen at the cathode and oxygen at the anode. The half reactions at the electrodes are shown in equation 3 and 4. Even though green hydrogen is the cleanest form of hydrogen with the least negative impact on the environment, it accounts for less than 1% of the global hydrogen production. This is because green hydrogen has the highest production cost at 2.7 to 6.8 USD per kg, due to the considerable amount of electrical energy needed for water electrolysis. Electricity cost is an imperative factor for green hydrogen production costs. The 4 main technologies available for green hydrogen production from water electrolysis are alkaline electrolysis, protein exchange membrane, solid economically using fossil fuels together with CCS, that is blue hydrogen, well until 2050. BNEF has estimated that green hydrogen production from 0.8 to 1.6 US kg by 2050. By 2035, there should be an abundant supply of renewable energy sources coupled with an increase in green hydrogen production. After this period, green hydrogen will become more cost competitive than blue hydrogen. So now I'm going to talk about the uses of hydrogen. The petroleum refining and chemical industry uses more than to support the implementation of hydrogen technologies has restricted its application across other industries. Hydrogen has the potential to decarbonize sectors with high industrial manufacturing, power generation, and buildings. It is predicted that by 2050, the hydrogen economy would exceed 2,500 Transport is one of the most promising and challenging sectors to decarbonize, since gasoline and diesel, petroleum products, account for 9% In the short term, hydrogen can be blended with petroleum products to improve the combustion efficiency and lifespan of internal combustion engines, as well as reduce CO2 emissions until the cost and efficiency of hydrogen-powered fuel cell vehicles and battery electric vehicles improve. In the long term, the implementation of FCVs, BVs, or a hybrid combination of both will support the decarbonization of the transport sector by further lowering CO2 emissions whilst improving local air quality and reducing noise. Note, more attention and investment need to be placed on hydrogen refueling stations, hydrogen grids, and hydrogen tankers in order to make hydrogen fuel more accessible and widely accepted. Globally, China has invested the most capital into hydrogen research and development and intends to have 1,000 fuel cell buses running for the 2020 Winter Olympics in Beijing. Since 2019, there has been 2 refueling stations operated in Shanghai, and there are plans to have a total of 1,000 hydrogen refueling stations by 2030. Japan, the first country to adopt a nationwide hydrogen framework, is aiming to have about 800,000 fuel cell vehicles, 1,200 fuel cell buses, and 900 hydrogen refueling stations in place by 2030. Additionally, Japan has been producing green hydrogen since March 2020 from its Fukushima Hydrogen Energy Research Field, which comprises of the world's largest class capacity water electrolyzer at 10 megawatts, and it can produce enough hydrogen to fill 560 FCVs per day. Presently, the industry sector accounts for most of the global hydrogen consumption, with around 55% utilized for ammonia synthesis, 25% in refineries for hydrocracking and desulfurization, 10% for methanol production, and 10% for others, example, steel making, fertilizers, cosmetics, and food processing. This industry is undoubtedly the most challenging to decarbonize due to large-scale integration, the lifetime of plants, which are usually 25 to 50 years, the global cost competitiveness, 45% CO2 emissions from the processing of feedstock, and 35% CO2 emissions from research and development is still required to increase the TRL of hydrogen in the industry sector. Ammonia is currently used to manufacture cost-effective hydrogen carrier and can be utilized in specific fuel cells or as fuel in internal combustion engines. In Australia, Yara and ENGIE will complete construction of one of the world's first industrial-scale renewable hydrogen plants in 2023. This green hydrogen plant will operate in conjunction with the current Yara Pilbara ammonia plant and deliver 3,700 tons of green ammonia per year to decarbonize emissions from mining explosives, shipping, power generation, etc. In Saudi Arabia, Air Products also plans to construct one of the world's largest green hydrogen plants, which will be powered by 4 gigawatts of wind and solar power. The $5 billion USD plant will produce 650 tons of green hydrogen per year. Green ammonia production will commence in 2025 and will be shipped internationally to end users before being converted back to green hydrogen. In Sweden, H2 Green Steel plans to construct the world's first ever emissions-free steel production plant. The green electricity required to produce green hydrogen and green steel one of the future largest onshore wind farms in Europe. The power generation sector accounts for 27% of Nonetheless, there are two promising applications. Firstly, hydrogen can be used as electricity storage via the power to gas, specifically the power to hydrogen concept. The green hydrogen that is produced from excess renewable energy is stored underground in depleted oil and gas reservoirs or overground in tanks, transported, and then reused for grid stabilization. This process is called power to hydrogen and is basically the conversion of electrical energy to chemical energy through hydrogen gas production. In 2020, the world's first power to hydrogen demonstration project commenced in Saillat-Savigny, France. Fired power plants. That is, hydrogen can be used as a feedstock for hydrogen power plants, which will generate clean and transmittable power. As of 2020, the worldwide natural gas-fired generation capacity was around 1,900 gigawatts. Turbine manufacturers Mitsubishi Power, GE, and Siemens Energy are presently working on developing turbines to run on 100% green hydrogen by 2030. It should be noted that in an effort to support the hydrogen transition, these companies have been blending hydrogen and natural gas to create mixed gas turbines in the interim. In the US, Long Range Energy Terminal is currently constructing a 485 megawatt combined cycle power plant that will operate on green hydrogen. It will be the first hydrogen burning power plant in the US, as well as the first to blend hydrogen in a GE hydrogen gas turbine worldwide. Another sector with potential hydrogen application is heating. Some projects have already started to explore the various hydrogen applications, which includes mixing hydrogen with natural gas, also known as heating, to heat residential and commercial buildings, replacing heating with 100% green hydrogen, and developing dedicated hydrogen boilers. In the UK, more than 30% of CO2 emissions originate from heating and cooking. H21 North of England is due to commence in 2028, and it will be one of the world's leading clean energy projects. It will convert 3.7 million residential and commercial buildings in the UK from natural gas to hydrogen, consequently reducing CO2 emissions and providing decarbonized heat. Hy4Heat is a program that investigates the potential utilization of hydrogen for heating residential and commercial buildings in the UK. In April 2021, the UK opened its first set of houses with hydrogen-powered household appliances in Low Thornley, Gateshead. In the UK, 8 out of 10 homes use natural gas boilers to power their central heating. Furthermore, inefficient boilers increase both natural gas consumption and CO2 emissions in the heating sector. However, replacing all the natural gas boilers with renewable heating systems would be infeasible and expensive. Consequently, a more practical solution would be to replace natural gas boilers with hydrogen boilers. From 2025, natural gas boilers will not be installed in new buildings in the UK. In 2019, the world's first 100% green hydrogen boiler commenced operation in Roseburg, Netherlands. The manufacturer of this hydrogen boiler, BDR Tamir Group, is currently partaking in a large-scale demonstration project in the UK. The goal is to install more than 400 hydrogen boilers by 2022. Now in this section, I will briefly analyze the 5 main factors affecting the energy transition from fossil fuels to hydrogen. The hydrogen economy will flourish when the cost of hydrogen, which includes its entire life cycle, that is production, storage, transportation, and utilization, can compete with the cost of fossil fuels. Currently, hydrogen cannot compete with both fossil fuels and renewable energy sources due to the high energy loss during production. Additionally, expensive electrolyzers plus platinum-based metals, which are required to manufacture most commercial fuel cells, have made the large-scale production of hydrogen more uneconomical. On the contrary, as the production cost of renewable energy continues to decline in the coming years and the supply of renewable energy becomes abundant, green hydrogen production will develop into a feasible option, granted that there is a decrease in the cost of electrolyzers. If the cost of electrolyzers continue to drop, BNEF calculates that by 2050, the production cost of green hydrogen will be between 0.7 to 1.6 USD per kg. This production cost is equal to natural gas price at 6 to 12 USD per MMBTU. Therefore, making green hydrogen competitive with natural gas on an energy equivalent basis, as well as cheaper than blue hydrogen. Hydrogen has a safety factor of 1 and is the safest fuel when compared to gasoline and methane, whose safety factors are 0.53 and 0.80 respectively. Still, hydrogen poses 3 main technical safety challenges. 1. Hydrogen is extremely light and flammable. Hence, it can easily leak and cause a fire, deflagration, or detonation. Hydrogen flammability is a function of its concentration level, and its flame is hotter and faster than that of other fuels. Hydrogen presents a risk in confined, unventilated spaces rather than open areas because the gas cannot easily escape, resulting in significantly higher overpressures. Explosion venting, such as pressure relief panels, can be used to decrease the effect of deflagrations in confined spaces. Also, hydrogen detectors should be installed in enclosed fueling operations to promptly detect leakages and ensure safe operations. 2. The auto-ignition temperature of hydrogen is 585 degrees Celsius, which is the highest when compared to other fuels, and is a positive safety characteristic. But in the presence of oxygen, this temperature decreases. Additionally, hydrogen's low electroconductivity rating is a concern since both liquid and gas flow, along with agitation, generates electrostatic charges which can potentially trigger sparks. Consequently, all hydrogen equipment should be electrically grounded. 3. There are 3 types of hydrogen embrittlement that occur in ferrous alloys. Environmental embrittlement that cause losses in ductility, surface cracks, deformation, and decrease in fracture stress. Internal embrittlement that generates internal cracks, plus hydrogen reaction embrittlement that creates brittle hydride. Hydrogen embrittlement can be prevented by coating techniques, plating techniques, selecting amorphous structure material, adding aluminum and titanium to base materials, as well as creating a barrier for hydrogen penetration by adding a carbon, nitrogen, and oxygen diffusion layer. Local and national governments equally play a crucial role in accelerating the growth of the hydrogen economy because of the substantial amount of capital involved, and the level of assurance mandated by lenders and sponsors to ensure successful project development. Governments can provide support through regulatory frameworks, deliberate and strategic programs, as well as by implementing policies and tax incentives which will create a market. Central government support can also be provided through government-funded research and development to develop hydrogen technologies and demonstrate their reliability. Public-private partnerships involving infrastructure developers, public investors, private investors, vehicle manufacturers, etc. Other government financial support mechanisms such as government guarantees, tax incentives, equity loan hybrids, preferential long-term loans, and financing schemes for first movers. And lastly, public procurement and fleet regulation. The government can boost hydrogen demand by procuring green electricity, heating, and vehicles, example, hydrogen buses, FCVs for government fleets. Fleet regulation can also create a demand for FCVs, minimize the entry barriers for first mover companies, as well as assist in scale-up efforts for infrastructure developers and vehicle manufacturers. Furthermore, the adoption of climate policies such as carbon taxes, zero-emission zones, and emission trading schemes by governments can have an indirect impact on assisting in the development of the hydrogen economy. Hydrogen infrastructure refers to the physical links between hydrogen production, storage, distribution, and usage. It includes long-distance pipelines, transport by water, rail, and road, sizable hydrogen storage facilities, and filling stations. The lack of hydrogen infrastructure and the significant cost of building one, coupled with insignificant hydrogen demand, is a major hindrance for the ongoing energy transition from fossil fuels to hydrogen. Hydrogen infrastructure is mandatory to support the adoption of hydrogen technologies in all sectors as well as a hydrogen economy. It should be noted that quite a few natural gas infrastructures can be converted to hydrogen infrastructures with very little investment. Likewise, in order to increase the widespread adoption of FCVs, hydrogen refueling stations must be accessible. This is simply only where FCVs are concentrated. Example, forklifts at warehouses and at airports for towing vehicles. The public perception of hydrogen is of vital importance in the energy transition. At present, hydrogen is not an attractive fuel due to being perceived as dangerous and explosive. It has a history of being involved in serious industrial accidents that resulted in major societal and economic costs. The first accident occurred back in 1937 when a hydrogen-filled Hindenburg Zeppelin in New Jersey exploded. Although it was publicly stated that the material coating caused the explosion, hydrogen took the rap. 3 other accidents listed in the literature are a hydrogen release during maintenance in Houston in 1989, the rupture of a pressurized hydrogen tank in Frankfurt in 1991, and a hydrogen explosion in Air Products and Chemicals Inc. in California in 2019. These accidents have been assiduously investigated and resolved with solutions put in place to prevent further disasters. The transition from fossil fuel to hydrogen can not only be seen as a techno-economic, but also social, because different societies share dissimilar views on the implementation of new technologies. Effective public education will be the driver in gaining widespread acceptance of hydrogen technologies. The program should include the aim of hydrogen economy, that is, to achieve a carbon neutral society, and the feasibility of attaining it. Moreover, it should speak the language of the participants it is geared towards and be sufficiently persuasive to receive support. The public wants to know how the different applications of hydrogen will affect their lives. Therefore, a variety of studies related to the possible hydrogen economy scenarios is compulsory. Notably, government investment in developing innovative hydrogen technology would improve partially constructed hydrogen infrastructures subsequently, solidifying a positive social standing for hydrogen. Globally, several countries are making considerable efforts in the research and development of hydrogen technologies to accelerate the energy transition from fossil fuels to hydrogen. Some governments have implemented national programs using cutting-edge hydrogen technologies that have the potential to create a carbon-neutral society that will benefit future generations. Yet, several technical gaps still exist, and more research and innovation are required to develop solutions that are technically feasible and possible. To accomplish this, more collaboration is needed between governments, companies, universities, and organizations. Some areas where additional research and development is required in order to guarantee a safe and sustainable path for the hydrogen energy transition are: 1. Fuel cells. More research is needed to make commercial scale fuel cells cheaper, as well as to improve their performance and durability. Electrolyzers. More research is needed aimed at lowering the cost of electrolyzers and improving their efficiency. Also, electrolyzers should be designed to use seawater as feed instead of distilled water. Safety. For considerable headway, research into understanding hydrogen, taking into consideration its intrinsic properties, will be crucial in achieving a high degree of safety. Additionally, reliable and economic hydrogen sensors must be developed to protect systems employing hydrogen. Storage. Hydrogen storage possesses the biggest challenge for the hydrogen economy. Further research is needed in terms of effective storage systems, volume, size of tanks, material properties, chemical and metal hydrides, system configurations, costs, duration, hazards, leakage and ventilation, and speed of discharge. System analysis. Procedures need to be created and that focus on the development, demonstration, and deployment of hydrogen supply chain, considering the array of energy sources, renewable energy coupled with hydrogen energy transition pathways, production and storage technologies, infrastructure and the ecological, economical, and societal concerns. So now I'm going to look at some of the conclusions from today. So today's energy system is unsustainable. It is incapable of supporting continuous economic growth due to limited fossil fuel reserves, the decrease in cheap oil, the capacity of environment to absorb greenhouse gas emissions, and the increase in energy demand. Hydrogen is a non-toxic, clean-burning, versatile, and efficient fuel with the potential to improve energy security while reducing greenhouse gas emissions. Nevertheless, the world still has a long way to go before transitioning to a completely developed and operational hydrogen economy. The transition from fossil fuels to hydrogen is progressing in phases, from gray to blue to green hydrogen. The world is currently in the blue hydrogen phase. also known as the bridging phase, where stakeholders are exploring the synergies between the oil and gas industry, gas reserves, CCS resources, reusing existing infrastructure, and the renewable energy industry before a full transition to green hydrogen. The scale-up of renewable energy sources is allocated to decarbonizing the present power sector. However, the power capacity of these renewable energy sources is not sufficient to support clean power generation and the expected increase in hydrogen demand. Consequently, blue hydrogen is needed to satisfy the increase in hydrogen demand during the transition phase, as well as to solve the integration of hydrogen with natural gas networks and design storage facilities that will support grid stabilization capacities. Governments will play a crucial role in strengthening the hydrogen economy. Nowadays, the cost of hydrogen and scaling up hydrogen infrastructure is considered too expensive when compared to fossil fuels. For this reason, governments must include the development of hydrogen projects on their political agendas and provide the necessary support through regulatory frameworks, deliberate and strategic programs, as well as by implementing policies and tax incentives. Also, the hydrogen value chain encompasses an array of sectors: transport, industry, power, and heating, plus end users, with the possibility of creating employment for more than 30 million people globally by 2050. The hydrogen energy transition is still an unfamiliar territory. It will take decades to transform hydrogen into a sustainable energy carrier that will mitigate the effects of greenhouse gas emissions, as well as improve energy security. The oil and gas industry is well positioned and has the necessary resources and technical capabilities to continue to drive the hydrogen energy transition on a global level. If stakeholders continue along the current path that they are on today, it is estimated that green hydrogen could potentially meet around 25% of the world's energy demand by 2050. I would like to thank SPTT, SPE UWI, and everyone who attended the technical talk today for the opportunity to share my knowledge on hydrogen energy. I hope it was a beneficial session for everyone. Thank you.
Thank you so much, Ms. Dewan, for such an educational presentation on hydrogen energy. We appreciate having the workings and the use of this upcoming sector explained. I would like to take this time to start the question and answer session in case anyone in the audience has any questions. So you can raise your hand and then unmute your mic. So if anyone has, you can just unmute. Okay, well, I actually may have a question. So do you think that there are any problems with using hydrogen on such a massive scale to be able to supply an entire country with energy?
So I don't think hydrogen, especially now, it's possible to do that because there's, as I said, a lot of research and development that still needs to be done, especially in terms of safety. But let's say a couple of years down the line, let's say maybe 2050, 2060, it will not only just be hydrogen energy that would be used, it will be a combination of both renewables and hydrogen energy. Moving forward with the energy transition, we will not only need one source of energy or one source of fuel. It'll be a combination. So when we talk about renewable energy, we talk about solar, we talk about wind, we talk about hydro, right? So we need to also be developing these different sectors. And then when we are producing more renewable energy that we need, for example, we look at solar panels, and some areas have summer, some areas have winter. So maybe during the summer, some areas will produce more energy than they need. So the idea is to take this energy, this excess energy, convert it into hydrogen and store it. And then when the winter time come, you convert that hydrogen energy back into electrical energy to be used.
Thank you. Does anyone else have any questions they would like to ask? You can just unmute your mic. Yes, Mr. Alasfor, you could go ahead.
Hi, thank you for the informative presentation. My question is around what do you perceive as the main challenges in transitioning into the ultimate goal? From what I saw that your presentation, it was the green energy. So where is the period that, or what is the main challenges to get us to blue, from blue to green?
Okay.
So, in terms of research specifically.
Okay. So in terms of transitioning, honestly, I think there's a lot of research being done, especially in the Middle East and in Europe. The challenge, I think, especially talking from a regional perspective, so in Latin America and the Caribbean, will be government policies. Because the reason why so much advancements are occurring in Europe region, or even in the Middle East region, is because the governments are pushing it. They are driving the energy transition. They are putting the policies in place. The companies as well are driving it. We see a lot of organizations coming together. I think this week in the Middle East, we had Total partnering with Siemens Energy, right? Partnering as well. So the main challenge would be, I don't think it would be research, because a lot of research is being done in those regions. The main challenge would be government policies or governments themselves, and maybe funding, or in the third world countries, if they will be able to support to make this transition.
Thank you.
Yes, thank you. I also see another hand from Mr. Balan Singh. You can go ahead.
Hi, good afternoon. Hi, Cassandra. How are you?
I'm good. Hi, Amit.
Yeah. Okay, so I had a question in relation to, I don't know if you have any further information on the new gen plant and the project with the hydrogen plant being built in Trinidad. Do you have any update on that or any information?
I don't want to talk on that. Okay, no, I don't have anything. I'm not involved in that. I know some issues have been raised. You remember Samuel? He used to work on UN with me. He was my technical manager. And he raised an issue: why isn't it being designed by us, Trinis, or why aren't we more involved in this? Why is it being outsourced? And again, it's a big problem in Trinidad, right? We think we don't have the expertise or the knowledge to do these things, and we tend to look at, I know we have some first world country people here, but we tend to look at the first world country. We tend to go to Europe or those other places and use their companies and their resources. And in Trinidad, we just operate. Classic example, we have the ammonia plants in Trinidad, right? How many ammonia plants? And we could be using renewables or doing pilot hydrogen projects. I think this week we actually now partner with BP to do CCS. Carbon capture and storage has been a big problem or issue in Trinidad. We have a pipeline running from the estate down to south that deteriorated. And again, it comes back to government, it comes back to policies, and we in Trinidad, we need to stand up for ourselves as well and push to be more involved in these projects. Or yeah, it's a political problem in Trinidad.
Okay. Thank you. I also see a question from Crispin R. Andrews. You can go ahead.
Hi, good night. Thanks, Cassandra, for the presentation. Although I missed a bit of it, I kind of dropped off. I have one question. I think it's more specific to Trinidad. I'm from Grenada, and in Grenada, the price of energy is quite high. You can say about 90 Eastern Caribbean dollar cents. Compared to Trinidad, it's about 10 cents Eastern Caribbean dollars. I think one of the problems that we have moving forward, particularly for Trinidad, where the fuel is subsidized in terms of bringing on renewables. I mean, what would be the benefit in terms of that? Hello, you hear me?
Sorry, Crispin, I think I missed part of what you're saying. Can you please repeat the question?
Okay, let me check out.
It could be my network. It doesn't have to be you.
You hear me now?
Yes, I can hear you. Yeah.
Okay, sorry. Yeah, so in terms of the pricing for the price of energy in Trinidad, I don't know what you would suggest, but in terms of making renewables viable, because when we look at hydrogen, personally, I think green hydrogen is the way to go. But in terms of getting people on board, considering the socioeconomic factors, would you say, well, let's stop subsidizing the fuel for us to get to that level? Because then we have to drop the price of renewables below that of fuel to make it.
Change is the fuel subsidy. And that is where governments come in and policies coming as well. But something that we lack in Trinidad is renewables, right? A wind study. And I think today they're still trying to push for that study with the Ministry of Energy. However, in Guyana, they've been able to do this study, right? They're currently doing wind study. In St. Lucia, they use a lot of solar panels to generate heated water, or sometimes even electricity. I know the same in Guyana. Everything operates on solar energy, right? So a lot of the problems we have in Trinidad is because we have oil and gas. And we've been programmed for the last 100 years, and we don't have an appreciation for simple things. And now I think it's our generation, the generation below us, that needs to push for renewable energy and push for hydrogen and push with the Ministry of Energy, right? There's a lot of bureaucracy, even we need to get the talk going. I think even this new hydrogen plant being built in Trinidad is one way of getting the talk going and the momentum. And as we start talking more about it and doing more studies, these recommendations.
Okay, thanks a lot for that. That was very insightful. Because I actually did my bachelor's in Trinidad and UWI, and it was a culture shock for me because in Grenada, you take off the lights once you're not using them. But while I was in Trinidad, people seem to be just leaving them on because the energy cost was so low. So it was a big shock for me.
I think he may have dropped off there.
Islands like Bahamas, I think Bermuda, some of those other islands have a very strong program in place when it comes to renewable electricity.
Hello?
Hi, Cripson. I think you keep dropping off, so we keep losing
sorry
you.
about that. Sorry. Yeah, I was just saying
fine.
that I did my bachelor's at UWI, so the culture shock for me was everyone having on their lights in Trinidad, and no, in Grenada we scramble to take off the lights. But yeah, so I do understand that. But thanks for that insight there. I'm gonna give
You're
someone else
welcome.
a chance to talk or ask a question.
Thank you for the question. I think you see we have another question from Felipe Cruz, Adrio Cruz. You can go ahead.
Hey, Cassandra. First of all, thank you for the presentation. It was very, very thoughtful. I have a question. You mentioned the part of the hydrogen storage, right, as one of the requirements for the industry to change. How do you think the oil and gas industry can benefit from storing hydrogen in, I don't know, maybe depleted reservoirs? Do you think there is a way that the oil and gas industry can use these reservoirs as assets for hydrogen storage?
Felipe, sorry, I lost you for a bit. My connection, I think, is bad. You can repeat it?
No, just that you mentioned that the hydrogen needs to be stored, right? And I was just thinking that depleted reservoirs, oil and gas reservoirs, could be potential storage places for hydrogen in the subsurface. So how do you think the oil and gas industry can adapt and benefit from their assets, reservoirs, as a hydrogen storage container?
Okay, so the entire idea is that the oil and gas industry would turn into our renewable or hydrogen economy, right? The oil and gas industry will always exist. It's not going to disappear. But we need the help of the expertise in oil and gas in order to make renewable or hydrogen energy possible. Like right now, where we are finally getting to the point of using the depleted reservoirs for CCS. And more research needs to be done on how we could do the same for hydrogen. So there the pipelines, and we could use the same natural gas pipelines, or the other option is storing underground and then again using your natural gas pipelines to send to homes or
Thank you, Cassandra. Thank you for the explanation.
Thank you.
Thank you for the question. I'm not seeing anybody more hands raised, but if anyone else has a question, you can raise your hand now. Yes, Ms. Gemma, go ahead.
Hi, June. Hi, Cassandra. Really good talk. Thank you for sharing with us. I just had a quick question. I was wondering, you mentioned policies were important to get the technology and the technology going per se. What sort of policy measures do you think governments in the Caribbean could actually apply to drive hydrogen as a technology within the region?
In terms of Trinidad case, one is our subsidy, obviously, on oil and gas. And then two is in terms of doing more studies, the funding to do more studies on the to do in Trinidad. You need the approval of the ministry because you're putting equipment down and whatnot, but you also need funding, which is difficult to get. And then we in Trinidad, for example, how the different countries, Germany have, Europe have, even Japan and China have. So I think in Trinidad, the first thing we need to do is develop a roadmap 2060, because I think the US, they have some stuff pushed to 2060 because they can't meet certain targets. And then from that study or from that roadmap, we will be able to determine exactly what policy
Fantastic, thanks. I like the concept of the roadmap. Thank you.
Thank you, Suzanne.
Thank you for your question. Okay. I am not seeing any more hands raised, so I think that could be the end of our question and answer session. I'd just like to thank you again for the presentation, Cassandra. It was very informative, and I'd just like to remind everyone that this session was recorded, so if you would like to review the presentation, you can check it on the YouTube channel. We will send out the link to everyone.